Hello children, we are revising chapter number 10, light, reflection and refraction. In the previous video lesson, we discussed about the reflection part of the lesson. Today we are going to continue with refraction of light. So when light travels obliquely from one transparent medium to another, it gets bent, and this bending of light is called as refraction of light. Now there are two medium for light to travel and refraction to happen. One is rarer medium and one is denser medium. The medium in which speed of the light is faster is rarer medium, and in denser medium speed of the light is comparatively slow. When light travels from rarer medium to denser medium, it bends towards the normal. Let's understand this from the figure given below. Have a look at this. Imagine that the ray of light travels only in one medium. So if it would have traveled only in one medium, it would have traveled straight like this. But when it travels from rarer to denser medium, it bends towards the normal. Look at this. This is the normal and light has bent towards the normal. And this is how it has bent. Now when the light travels from denser medium to rarer medium, it bends away from the normal. Have a look at this. This is the ray. If light would have traveled only in one medium, it would have traveled straight. But because now light is traveling from denser to rarer medium, it will bend away from the normal. This is the normal, and look at the extent it has bent away from the normal. Alright, so these two rules you have to keep in mind. Now refraction of light through a rectangular glass slab. This is an activity which we are going to perform in our physics laboratory also. When the ray of light passes through a rectangular glass slab, it gets bent twice at the air-glass interface and the glass-air interface. Now interface is a place wherein the two media interact. Now just consider that this is a glass slab. But suppose if there is no glass slab kept anywhere, then the ray of light would have traveled straight like this. Alright, but now because the glass slab is placed, light is traveling from air to glass medium. So light is traveling from rarer to denser medium, so it will bend towards the normal. Now at this interface, at glass air interface, light is traveling from denser to rarer medium, so it will bend away from the normal. These are the two normals. This is first normal, this is second normal at glass air interface, and the first normal is at air glass interface. The angle made by the incident ray with the normal is called as angle of incidence, and the angle made by the refracted ray with the normal is angle of refraction, and the angle made by the emergent ray with the normal is angle of emergence. Alright, so three angles we have marked. Now can you see this difference? This difference of the refracted ray, this is the lateral displacement. It is, the light would have traveled straight if it would have traveled in a same media. But because we have kept the glass slab, the ray of light has displaced with some distance, and this displacement is lateral displacement. Then next is laws of refraction of light. Like how we have learnt about laws of reflection of light, now refraction of light. The incident ray, the refracted ray, and the normal to the interface of the two transparent media at the point of incidence all lie in the same plane. Second law is the ratio of sine of angle of incidence to sine of angle of refraction is constant, and this is constant for the light of given color and for given pair of media. This is also called as Snell's law. So sine of I upon sine of R is equal to constant, and this is called as Snell's law. Now in the figure, if you can see, the light is traveling from rarer to denser medium, from medium 1 to medium 2. But in terms of symbol, how will I write? N stand for the refractive index. So we will always write like this: refractive index of second medium with respect to first is equal to sine I upon sine R, and this is called as Snell's law. Alright, now let's understand what is refractive index. The refractive index of medium 2 with respect to medium 1 is the ratio of speed of light in medium 1 to speed of light in medium 2. In very simple language, I must tell you that when we say refractive index, it is the extent to which light bends in particular medium. How much bending of light is there from one medium to other medium, that is shown or denoted by refractive index. So refractive index of second medium with respect to first is speed of light in medium 1 upon speed of light in medium 2. V1 is speed of light in medium 1, V2 is speed of light in medium 2. Then there is something called as absolute refractive index, and the absolute refractive index of the medium is the ratio of speed of light in air or vacuum to the speed of light in the particular medium. So refractive index or the absolute refractive index is equal to speed of light in air or vacuum upon speed of light in medium. So N is equal to C upon V. C stands for speed of light in air or vacuum, and V is velocity or speed of light in the medium. The next is spherical lenses. Children, I would suggest for the detailed information about spherical lenses, you must watch our previous videos wherein the making of spherical lenses are explained in detail. So spherical lenses is a transparent material which is bounded by two surfaces, one or both of which are spherical. The spherical lenses are of two types. They are convex lens and concave lens. So convex lens is thicker at the middle and thinner at the edges. So if you hold it in hand, you will feel this. In case of convex lens, when the rays of light falls parallel to each other on the convex lens, after refraction, these rays of light, they converge at one place on the principal axis. This point is called as focus of convex lens. Concave lens is thinner at the middle and thicker at the edges. Now when the rays of light falls parallel to each other on a concave lens, after refraction, all these rays, they diverge, but it appears as if they are emerging from one point on the principal axis, and this point is called as focus of concave lens. But imagine that the rays of light are falling from the other side, from right to left side on the lens. In that case, the focus will be on the other side of the lens. Meaning is that every lens has two foci, two radii of curvature and two center of curvatures. Now, like how we studied about the rules to be followed to draw the ray diagrams, in case of spherical lenses also we have to follow certain rule. So when the ray of light is parallel to principal axis, after refraction, this ray will always pass through the second focus of the convex lens, that is denoted by F2. if you can see there on the principal axis, first focus f1 to the left side, second focus to the right side. 2f2 is double the length of f1 and f2. So 2f2 and 2f1 can be center of curvature also. Now in case of concave lens, when the ray of light is parallel to principal axis, after refraction it diverges and it appears as if it is emerging from focus f1. So this will be the first rule we will follow to draw the ray diagram for the spherical lenses. Second ray we can use this, the ray of light which passes through optical center and after refraction it goes undeviated, and the same case in case of concave lens also. There is third ray also. Third ray is when the ray of light passes through the first focus of the convex lens. After refraction it is parallel to principal axis. In case of concave lens, this ray of light is directed towards the focus and after refraction it is parallel to principal axis. And again the same thing, out of the three rays we can use any two rays to draw the ray diagram to find out the position of the image of the object. So let's discuss this. Images formed by convex lens, and this was the doubt of one child, and please have a look at this. When the object is placed at infinity, look at this, the object is placed at infinity, where will be the image? Now as I told you that when the object is at infinity, the rays of light coming from infinity appears parallel to each other. So these rays, they converge at one place on the principal axis, that is at focus f2, and here is a place where the image is formed which is highly diminished, real and inverted. Then the second position of the object, when the object is beyond 2f1. So let's place the object beyond 2f1. As I said, 2f1 and 2f2 is a distance which is equivalent to center of curvature. Every lens has two center of curvature and we are denoting that by 2f2 and 2f1. So object is beyond 2f1. Let's apply the rules. First ray parallel to principal axis, after refraction passes through focus f2. Second ray, the ray which passes through optical center and goes undeviated. These two rays meet at one point and there is a place where the image is formed. Look at this. So the image is formed between f2 and 2f2. The image is diminished, it is real and it is inverted. You can compare the size of the image with the object. Image is diminished. Next is when the object is at 2f1. So let's understand where the image is formed. Let us apply the rule. Ray of light parallel to principal axis. After refraction it passes through focus f2. Second ray passes through optical center, goes undeviated, and here is the place where the image is formed. If you see this image, both the object and the image are of same size. The image is real and inverted. Alright. Then when the object is between 2f1 and f1, so let's keep the object between 2f1 and f1. The image is formed at which place? Let's apply our rules. Parallel to principal axis is the first ray. After refraction passes through focus f2. Second ray, the ray which passes through optical center which goes undeviated, and the image is formed at this place. The image is formed beyond 2f2. It is enlarged, it is real and inverted image. Next position is when the object is at f1, at focus f1, the object is placed. Let's see where the image will be. So the first rule, the ray of light parallel to principal axis. After refraction, it passes through focus f2. Second ray passes through optical center and goes undeviated. If you observe both the refracted ray, they are parallel to each other. They do not meet at any point, so the image is formed at infinity. It is highly enlarged image. It is real and inverted. Alright. Next is when the object is placed between f1 and the optical center. So here is the place of the object. So our first rule, the ray of light parallel to principal axis. After refraction, it passes through focus f2. Second ray is the ray which passes through optical center and goes undeviated. Both the refracted rays are not meeting at any point, but if we extend these two rays behind in the backward direction, they appear to meet at one particular place, and that is the place where the image is formed. If you compare the image with the object, you will observe that the image is enlarged, virtual and erect, and this is the only position of the object wherein we are getting virtual and erect image. Otherwise, for all other places, we are getting real and inverted image of an object. So this particular place of the object you have to keep in mind. Alright, next is the images formed by concave lens. So when the object is placed at infinite distance, the rays of light, they appear to come parallel to each other. After refraction, these rays diverge, but it appears as if they are coming from the focus on the principal axis, and there is a place where the image is formed, which is highly diminished, virtual and erect. But now suppose if you keep the object between infinity and the focus f1, anywhere between infinity and focus f1, let us apply the rule. First ray parallel to principal axis. After refraction, it diverges, but it appears as if it is coming from the focus. The second ray passing through optical center and goes undeviated. And can you just check out this place where both the rays meet each other? That is the place where the image is formed. And the image is formed between f1 and optical center, and the image is diminished, virtual and erect. So for concave lens, you can place the object anywhere between infinity and focus, and you will always get the image between f1 and optical center. The image will always be diminished, it will be virtual and an erect image. Alright. Then the sign conventions for spherical lenses, and this is exactly similar to how we discussed for the spherical mirrors. So in spherical lenses, the optical center we have to consider as origin, and all distances towards the left of the optical center are negative, and the distances towards the right side of the optical center are positive. Distance above optical center is positive and distance below optical center is negative. So object distance for spherical lens, convex lens you can say, or concave lens, for both the lenses, object distance will always be negative because object we keep on the left side of the lens. And image distance and image size depends upon whether the image is real and inverted or the image is virtual and erect. So the graph you have to bring in front of your eyes, and accordingly sign conventions you have to follow. Then considering the focal length for the convex lens, for convex lens focal length is positive, and for concave lens focal length is negative. So you have to just imagine which side of the optical center the distances are, and accordingly you have to follow the signs. Alright. Next is the lens formula for spherical lenses. Now the relation between object distance, image distance and focal length is given by 1 upon V minus 1 upon U is equal to 1 upon F, and this is called as lens formula. So do not get confused between the mirror formula and the lens formula. You have to learn this carefully. Alright, after that, the magnification produced by spherical lenses. So magnification of spherical lens is the ratio of height of image to the height of object. So magnification is denoted by letter M, which is equal to height of image to height of object, and we can also write this as h dash upon h. And magnification is also related to object distance and image distance, and it can be expressed as M is equal to h dash upon h is equal to V upon U. Alright, the two formulas for the mirrors and lens, you have to be very clear. Do not get confused with the sign, positive or negative signs. Alright, so these are all the important points of the chapter, and based on all these important points, you have your first periodic test, which is in the form of multiple choice questions. So read the questions carefully and tick the correct option. All the best, and see you all in the next video lesson.